Okay, dear students, so let us see what is there in this question now. A beam of coherent monochromatic light is incident normally on a single rectangular slit. The diffraction pattern is observed on the screen. Okay, so there is a single slit. Obviously, there will be diffraction. O is the point on the screen directly opposite the slit. P and Q are the first minima on either side of the central fringe of the diffraction pattern. The intensity of light at point O is I naught. So the total intensity, maximum intensity given as I naught. The distance of OP is X. So X is the distance for the minimum intensity there. Sketch on the axis a graph to show the variation of intensity of light with the distance from point O on the screen. Your graph should cover the range of 0 to 2x. Okay. So, as per the information given here, diffraction is taking place, and O is the point where the maximum is coming. Like, let us say this is the maximum intensity that is happening, and the intensity will be I naught. Although the value is not given, and like there will be no formula also, so we can just write it as I naught. P is the point where their first minima is occurring, so it will go somewhat like this. Okay, so this is P and this distance is X. Clear? Now after this, the point to be noted now is, although for the central fringe the fringe width becomes 2x, isn't it? X up and X down, so the total fringe width is 2x, but the fringe width for the very next fringe, it will be half of this. What do you mean by that? This is X, and let us say this is an equal distance, this is again X, so there will be a minimum here, so it will be like this. You got it? Although this central fringe, which is maybe maxima, the thickness of that is coming out to be 2x, but the thickness for all other fringes is half of that, which is x. So this is 2x and this is x. This is the point to be noted here. And you want to draw a graph from with respect to O. So this distance will be x up to P, and this distance, let me call this point as A. So if we talk about O to A, so the total distance will be 2x, isn't it? Because this is also x. Yeah, from O, this is x and this is also x. Now the question wants you to draw the graph between the intensity and the distance up to the point A. Let us see how are we going to draw this. So this is the graph here. So the intensity is given as I naught for the maximum for the central fringe. It is I naught, and the minimum is at x. So clearly you would be moving somewhat like this. And after that you have to, there will be a minimum on 2x also, and the midpoint of that 1 2 3 4 5. So the midpoint is this. There will be the maximum value there. Now, how about the maximum value here? How can we find that? So this maximum value will be somewhat like this. See, the minima will be a lot lesser than this. So you cannot draw it like bigger. It has to be lesser. So my advice will be you can just draw like this. But it should not be very high. But there is no method in which you can actually find the intensity of this maxima. This intensity you cannot find with any formula. This intensity, fine, it is given there. So this is it that we have to draw, and I think this will be the answer. Let us see the mark scheme once and how are they doing it. Yeah, 7-1A. Yeah, here it is. So you can see that the graph starts from the I naught, it goes to 0 at x, and then it goes like this. So this value is very small, and they have written here is that the intensity is less than 0.3. It means it will be lesser than 30% of the total intensity. So it could be anything. You can draw it 1%, 10%, you can draw it 20%, but it should be less than 30%. And there is no rule as of like as such, but usually it is like that. There is no mathematical formula to confirm this value, by the way. Okay, yes, let us now go to the next question. Early theories of light suggest that the geometrical shadow of the slit will be observed on the screen, because initially it was thought that the light travels in a straight line, and so if the light travels in a straight line, it should not encroach into the shadow area. Let me explain you this. Like this is the slit here, let's say, like this, and it is illuminated with the light, like this. The light is coming like this. So when it passes over this, if this is the screen, we imagine that the light is traveling in a straight line, so the light should move like this, and this area will be known as geometrical shadow area. Geometrical shadow area, as it is given here, geometrical shadow. So this is the geometrical shadow area. So it should be a shadow there if the light is traveling in a straight line. But it is found that light, instead of moving like this, it encroaches into the shadow area. So light is actually moving like this. It bends a bit and it goes like this. So this area is a gray area. We cannot say that it is black, like just like shadow. So there is some intensity that is coming to this point, although it should not be coming if light travels in a straight line. It means that light is definitely bending. And why is it bending? Now, this phenomena of bending of the light when it encounters the obstacle in its way, this phenomena is known as diffraction. Now the question is, explain how the diffraction pattern formed on the screen provides evidence for the wave theory of light. So this experiment, or you can say interference for that sake, diffraction and polarization, these are the three phenomena which can be used or which are cited to prove the wave nature of the light. And why is this a wave now? Because it is bending. If it was a particle, it will move straight forward and it will hit this point, and there is no way in which it will be bending. So if it is bending, it has to be a wave, and this phenomena can be explained only because of the interference, which uses the concept of the wave, and that you already know. We are using sine omega t's and all that. So definitely it is a wave. This is what we can write here. So many type of answers can be given, but let us see what is the answer that they have given. Observed pattern goes beyond the rectangular shape or the geometrical shadow area. Observed pattern shows maxima and minima. This is explained by interference or the superposition of waves, clearly proving that light is a wave. So there are three such phenomena: interference, diffraction, and polarization. Polarization is a phenomena which is in the syllabus for the May 2024. Like in the previous syllabus it is, but I believe in the new syllabus polarization has been removed. So if the new syllabus students are watching this thing, please do not be confused with the word polarization. Okay. Now let us go for the next question now. Wavelength of the light is given as 590 nanometer. Distance between the slit and the screen. Distance between the slit and the screen is 2.4. The width of the slit is 0.1 millimeter. Calculate the distance PQ. So PQ is the distance between the two minimas, like that minima and this minima, but we have a formula only for x. So the formula for x is lambda capital D divided by B in the case of diffraction, where lambda is the wavelength, capital D is the distance between the slit and the screen, and the width is written as B. So we would be using this, and this is X. But you want to find the distance between P and Q. It means the actual width of the central fringe, which is double of X. So you would be multiplying 2 here. Anyways, let us first find this. So wavelength will be 590. Anyways, we can skip the calculation part. So your answer for this will be 2x. And let us see the mark scheme. How are they doing it? Yes, even they have done the same thing. Angle of the first minima, it is lambda by D by B, and the width, and now they are multiplying it with the capital D also. At the end of the day, they are doing the same thing, so don't get confused. So it is lambda capital D divided by D divided by B, and then you multiply it with 2. That's it. So you would be getting the answer. You can use the calculators and you can see. Let us move to the next page now. Okay. The single slit is now replaced by double slit. So now we are moving into interference. The width of each slit in this arrangement is the same as that of the width in the single slit. It means the diffraction pattern is not changing. What do you mean by this? The B length. The B is not changing. So the diffraction minima like x, we found it to be lambda d by b. So this x is not changing. Neither the wavelength is changing, neither the capital D is changing, nor B is changing. So this is not changing. So X is not changing. Diffraction pattern does not change. But there are two slits now. So it's actually not the diffraction, but interference which is taking place there. So we will see. Outline how the intensity variation observed between the point P and Q will change now. So this is called the modulation of interference pattern. Modulation of interference pattern with diffraction pattern. With diffraction. So what is actually happening? So if I'm going to draw the graph here, let us say this is x and this was 2x. So the diffraction was somewhat looking like this. Let us say this. And we are concerned only up to 2x. So this time the interference will be there, and see this, these are the slits like this now. Okay, the interference is taking place. The width of the slit remains the same, but there is something called this is called the distance between the two slits. This is d. So when it comes to interference, d is more important, and we do not take into account this b. So the interference pattern, let me call it as y, the distance of the fringe width in the case of interference, that will be given by lambda d by small d. So definitely small d is bigger length than b. So if the denominator is bigger, y will be lesser. So the interference pattern will be somewhat like this, and then it will go up, it will go down, it will go this, then like this. Somewhere like this. So approximation I have drawn. So this kind of a pattern will be there. Now this is known as the modulation of interference pattern, which was supposed to be at the same height. Like the interference pattern was supposed to be like this, that every of the peak will be reaching the maximum point. But because of the modulation of interference pattern with the diffraction, everywhere you are able to find different intensity. So this is what we are going to do. Outline how the intensity is varying. Now, another point to be noted here is that now instead of one slit, there are two slits. Definitely the intensity is going to be better. So intensity is directly proportional to the square of amplitude. When there are two slits, the amplitude will become 2a. So final intensity will be 4 times the earlier one because it will be squared. So this is going to be 4 times, and the interference pattern is going to be modulated with the diffraction pattern. Another thing is that this is not going to change. This value of x, which was lambda capital D divided by B, this is not going to change. And what is y? This is x. What is y? Y is the distance between these two. This is called the fringe width. Now fringe width is occurring every time. So this fringe width is not like, this is y, and it is also same for all of the fringes. For all of the fringes, it is same. Interference pattern, the fringes are spaced equally, they have equal width, and that is given by this. I hope it is clear. Clearly x is greater than y, so much so that 2 or 3 fringes have been housed within x. So accordingly we can imagine it like this. So this is the answer for this. Let us see what is the answer given in the mark scheme for the B part. The intensity at O increases, fringes or the series of maxima and minima is there, like this kind of a diffraction pattern is there now. So this is the x, like this. Intensity is modulated with the diffraction. So as you go further away, the intensity keeps on decreasing. So you can write anything. Okay. Accordingly, our answer is done. Let us now move to another question now. The light source actually emits two wavelengths. Okay, so now it would be talking about the diffraction grating, I think. Yeah, diffraction grating is there because this is the only case in which we mix the wavelengths. Otherwise, whenever you are talking for the interference or you are considering diffraction, we always consider monochromatic light. Monochromatic light means that there is only one particular wavelength. So if you are having two wavelengths there, they are mixed there, you are definitely talking about diffraction grating. There are a couple of formulas for that. Let us see. The average wavelength is 590 nanometer. There is this formula of the resolution, lambda average divided by delta lambda, it is equal to m into n, where m is the order and n is the number of lines illuminated. I will tell you this. So the wavelength is given, average wavelength. The difference between the two wavelengths is also given. So directly delta lambda is given and lambda is given. So this value is given to you. Student attempts to resolve the wavelength using a diffraction grating with 750 lines per millimeter. 750 lines per millimeter. The incident beam is 2 millimeter wide. So the total length is given as 2 millimeter. So how many lines have been illuminated? Definitely it is multiplied by 2. So that will be 1500 lines. So 1500 lines are there in the diffraction grating. What is happening is, let me explain you this. Diffraction grating is somewhat like this, and there are these lines, like this line. These are all slits that we have done in the case of the diffraction and the interference just now. But in this case, earlier there were only two slits in the interference. Now there are 1500 slits. So these 1500 slits are creating this kind of a pattern. Comment on whether this diffraction grating can resolve the wavelengths in the first order spectrum. What do you mean by first order? Now, first order is somewhat like this. So let us say this is the pattern that you are creating. Like this is the maxima, and this is the another maxima. Like I'm talking about the interference pattern now. So it's like this. So usually when we say this is the first when we say this is the first maxima, so there will be a first maxima downwards also. This is also the first maxima. This is again first maxima. This is again first maxima. These are the two first maximas. So these two first maximas are there. So when we want to refer to both of them simultaneously, we do not call them maxima or the first maxima. We call them first order. First order means that I want to talk about this as well as this. That is why we use the word first order. So first order means that m value will be equal to 1. Okay. And we want to see this. So let us see this thing now. Let me clear the space. Formulas are all clear now. So let us see. Lambda average by this. What is the value that we are getting? Lambda average is 590 10 raised to power negative 9 divided by 0.6 nano. Nano and nano gets cancelled out. So it is coming out to be 590 divided by 0.6. Okay. And what is the value coming? 5900 divided by 6. Sorry, I don't have the calculator as of now. Anyways, let us calculate the m into n also. So the first order is 1. And what about the n? N is 1500. So this is coming out to be 1500. Okay. So this should be, this is like 1500. This should be more. So if this is more, like m into n is more, like more number of lines are illuminated, isn't it? So the resolution becomes better. So to resolve this value should come lesser than 1500. If that is the case, the values will be resolved, the wavelengths will be resolved. Do you get my point? M into n, like first order, it is the function of our device, and n is also the function of the device, isn't it? So this is what we control with the help of our device. So this is the resolution power, resolving power of the diffraction grating, and this comes out to be equal to 1500. And this value if it is coming out to be lesser than 1500, it will be resolved, otherwise it will not be. Now let us find what is the value of 5900 divided by 6. Let me see. So it is 983, and this is definitely coming lesser than 1500, and that is why we can see that yes, these they will be resolved. Okay, so this is how we do this question. I believe this should be clear. There could be some bit of disturbance in this video, by the way. I'm sorry for that, for the background noise and distractions. I will try to remove it, but anyways, so this is it. Let us see if there is any other question in this. But okay, now this is it. So see you in the next video. All the best. Bye.